So let's look at page 17, which is potential energy. We know we've been thinking about energy as the ability to do work. And we want to look specifically at potential energy. And potential can be think of, like if someone might say, oh, you've got a lot of potential for being, like a good swimmer, or you show potential for art or something like that. So it sort of means that there's something there that hasn't necessarily been expressed yet. So it's present but not active. And in the context of mechanical energy, so this is all about moving things. Potential energy is one part of it, and kinetic energy is the other. And we'll talk about that a little bit later. But let's just focus on what's potential. And potential's all about height. So if I have a rock on the edge of a cliff, it's not moving, so it doesn't look like it has much energy at the moment, but it does have the potential to do work if it falls off the cliff there. So there's not very much stopping it from potentially doing work. Whereas if I had a similar rock down here at the base of the cliff, well, it really doesn't have the potential to do any work because it's on the lowest point there, and it's not moving, so it hasn't got any kinetic energy. So this one here has potential. And we know that if work is equal to the force times displacement, in this case, and I can also write it as mass times acceleration times displacement, then we know that the acceleration in this case for potential energy is going to be due to gravity. So we can change that out and write in a g. So we've still got our mass as little n, and we've got a g, and we often express this as the displacement as delta h. Okay, so that's the change in height. So we're using h because we're only talking about vertical motion, and we're going to say the h represents height. So this is then we're going to call this potential energy. So we have our E with a subscript P for potential energy. This formula, I believe, is on your formula sheets. E equals mg delta h. Yep. So the mass then is the mass of the object. We know that g is then equal to negative 9.81 meters per second squared. But if we're calculating energy, remember it's scalar, and so we don't need to worry about the sign anyway, by and large. And this here is then our h. Okay, does that make sense? And if we look at worked example 3.1, it tells us that there's a person whose mass is 50 kilos, walks from the ground floor to the second floor of a building 12 meters above, so delta H is equal to 12 meters. What is the person's gain in potential energy? So it's going to be about 5.9 kilojoules. In the booklet, it's just got 9.8 here instead of 9.81. You should use the value on the formula sheet, so that's 9.81. And worked example 2, it's not really a worked example, it's just a note. That is that, like I said before, it doesn't matter how you get up there. So option A, the person is just walking up the set of stairs to a certain height. And in the second example, half stairs and half ladder. So it's harder to climb the ladder than it is to climb the stairs. However, you've got the same potential energy no matter how you got there. Right, so it's not dependent on the path. Alright, and then there's one more example on page 18. How much work is required to lift a 2 kilogram mass? So this time our mass is 2 kilograms. From a height of 50 metres to a height of 60 metres, so delta H will equal 60 subtract 50, which is 10 metres. That's the change in height. And same formula. It's 2 times 9.81 times 10, which apparently is about 196 joules. So this is the energy, this is potential energy, and then we can say, therefore, the work is the same. Because the question asked for work, not just potential energy. Okay, so I'll let you get on with questions again. You could be finishing off set 4, or if you're up to it, you could be starting the questions in set 5.